Good morning, students. Sorry for the late start. So, yesterday we have discussed, we have found the expression for the equivalent capacitance of the capacitors connected in series. So, what expression we got in the yesterday's class? It is 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3. If three capacitors of capacitance C1, C2, C3, if we are using, then we get the equivalent capacitance as 1 by Cs is equal to. If just there are two capacitors, 1 by Cs is equal to 1 by C1 plus 1 by C2. So this, how can we do? If we take LCM C1 into C2, so this will be C2 plus C1, that I will write it as C1 plus C2 only. This is 1 by Cs. So that Cs is equal to, if you take the reciprocal of this, Cs is equal to C1 into C2 divided by C1 plus C2. Cs is equal to C1 into C2 divided by C1 plus C2. So this I can use this. So if three capacitors are there like this, so how it will be? 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Okay. So here the LCM is C1, C2, C3. Here it will be C2, C3, C1, C3. It is C1, C2, 1 by Cs. So that this Cs if we take the reciprocal, we take, write it as C1, C2, C3. If three capacitors are there, so we can write it with a little arrangement. How can I write? C1, C2 plus C2, C3 plus C3, C1. So this will be the shortcut if there are three capacitors. C1, if three capacitors are there, C1, C2, C3 divided by C1, C2 plus C2, C3 plus C3, C1. So if these capacitors are same, if they are same, in the sense here C1 is equal to C2, is equal to say some C, how it will be? Cs is equal to, so in place of C1 I substitute C, in place of C2 I substitute C, so it is C square. divided by, it is C plus C. So CS is equal to C square by 2S to C. So one of the C get cancels. CS is equal to C by 2. Similarly, here also if you do the same thing, C1 is equal to C2, E is equal to C3, E is equal to C. If you substitute here, the CS is equal to, so what we get, it is C by 3. CS is equal to C by 3. So if two equal capacitors are there, then its capacitance, equivalent capacitance is C by 2. If three capacitors are there, its equivalent capacitance is C by 3. Okay, so in this way, what I can write? If there are n capacitors, n equal capacitors, if there are n equal capacitors, in this series, n equal capacitors are connected in a series, so then the equivalent capacitance of this CS is equal to, it is C by n. In the sense, 4 equal capacitors are there, then it is C by 4. What is the capacitance of those 4 capacitors which are equal? So divided by 4, C by 4. So like this, how we got C by 3, C by 2. So in that way, if 4 equal capacitors are there, then it is C by 4. If it is 5 are there, C by 5. So these shortcuts we can use in solving the numericals. So what are the other things we have seen when the capacitors are connected in a series? So its equivalent capacitance, we got this. So this is the shortcut for those. So what other things we have seen is the charge on each of the capacitor is same. What is second point? What we have seen, the charge on each capacitor when they are connected in series, capacitor is same. Okay, what is the next point we have seen? So potential difference across capacitor across a capacitor is inversely proportional to its capacitance. inversely proportional to its capacitance. Okay. The next thing, this EMF of the cell, EMF of the cell, V is equal to, EMF of the cell V is equal to potential difference across each of the capacitor. Potential difference, it is EMF of the cell is equal to sum of the potential difference, sum of the potential difference across each of the capacitor. And one more thing you can see I'll explain it with one example. What it is? If the capacitance of C1 is equal to say 1 farad itself, C2 is equal to 2, C3 is equal to say 4. Okay. So 1 by CS is equal to 1 by 1 plus 1 by 2 plus 1 by 4. Okay, 4 plus 2 plus 1. So what it is? It will be 1 by CS is equal to 7 by 4. Therefore, CS is equal to 4 by 7. Just I have taken one example. So, equivalent capacitance of these, what I got? 4 by 7. So, what we can see here, the equivalent capacitance when the capacitors are connected in series is smaller than the 4 by 7 is smaller than the smallest among all the capacitors. Smallest is 1. This 4 by 7 is smaller than this one. The equivalent capacitance when they are connected in a series is smaller than the smallest among them. Smaller than the smallest among them. So this is one more point. What we can, equivalent capacitance when they are connected in series, equivalent capacitance is smaller than smallest among them. Smallest among the capacitors. It is smaller than the smallest among the capacitors that we have used to find its capacitance. So these are the points what we have observed in when the capacitors are connected in series. So these itself we can use in some of the exam. They will ask the difference between series and parallel combination. So these are the 5 points. Even the same 5 points we will get in the parallel also. So we can compare those things. So it is reciprocal of the sum of the reciprocal of all the capacitors. Charge on each capacitor is the same. Potential difference across the capacitor is inversely proportional to its capacitance. and the EMF of the cell is equal to sum of the potential drop across each capacitor, and equivalent capacitance is smaller than the smallest among the capacitors. So these things we have seen in this. So in this series combination, so what usually in the numericals, what usually they will ask? They will ask you to find the capacitance will be given, capacitance will be given to you. They will ask you to find out the potential drop across each of the capacitor. How it will be? If this is V, so capacitance is C1, C2, C3. So charge on each of them is Q, whereas potential difference is V1 here, V2 here, V3 here. So charge on this is Q, on this also it is Q, on this also it is Q. So usually by giving the capacitance and this EMF of the cell, they'll ask you to find the potential drop or potential difference between these capacitors. How you find this? So first itself we will take, already we have seen, it is C is equal to Q by V. So therefore V is equal to, it is Q by C. So for first capacitor, V1 is equal to, it is Q by C1. For first capacitor, we can write the expression as V1 is equal to Q by C1. So if I apply to the equivalent capacitance, how I can write? V is equal to, for equivalent capacitance, Q by CS. For equivalent capacitance, I can write it as, it is V is equal to Q by CS. So from this, get the expression for Q. Q is equal to V into CS. So that is substitute here. V1 is equal to, in place of Q, if you substitute V into CS divided by C1. So this will be your shortcut to find the potential drop across this. If since there are three capacitors there, what will be the equivalent capacitance? Just now I have written the equivalent capacitance. CS is equal to, it is C1, C2, C3. This is C1 I am taking here into, so what it will be? C1, C2 plus C2, C3. So this I take as a whole. C2, C3 plus C3, C1. So this is C1, this is C1, get cancels. So V1 is equal to, what it is? C C2 into C3 divided by C1 C2 plus C2 C3 plus C3 C1 into this. So this will be the shortcut to find the potential drop, potential difference on the capacitor C1. Similarly, I can write V2 as what it is here. In V1 there is no, in the numerator there is no C1. So similarly here there will not be C2 here. C1 C3 into V divided by C1 C2 plus C2 C3 plus C3 C. This will be the expression for V2. And the expression for V3 will be leaving C3. I have to write the expression in the sense it is C1 C2 into V divided by C1 C2 plus C2 C3 plus C3 into C. So in this way we can find the potential difference across each of the capacitor. Potential difference across each of the capacitor we can find out like this. And they'll ask you to find the charge. Once you know potential V1 C1, once you know V1, then V1 into C1 will give you charge. If just two capacitors are there, then in place of CS, you can substitute just C1 into C2 divided by C1 plus C2. Then C1 and C2, it will get cancelled. So based on that you can. If just two capacitors are there, in the same way you can find out. So V1 is, see what you are saying here, leaving that V1, we are leaving here what we got when we are doing the calculation. C1 get cancels. So C1 will not be there here. C2 into C3, leaving C1, C2 into C3 into the EMF of the cell divided by C1, C2 plus C2, C3 plus C3, C1. If just two capacitors are there, how it will be for two capacitors? V1 is equal to V into two capacitors. CS, what is our CS? For two capacitors, it is C1 into C2 divided by C1 plus C2 into this C1 you are writing here. So this C1 get cancels. So V1 is equal to, it is C2 into V divided by C1 plus C2. So similarly V2 will be, so leaving that C2 I have to write. So it is C1 into V divided by C1 plus C2. So these are the expression for potential drop, potential difference when just two capacitors are there, and this is when three capacitors are there, you can use this. So now we'll move to the next, the parallel combination of the capacitors. There we find the equivalent capacitance of the capacitors when they are connected in parallel. So it is parallel combination. Of capacitors. So how it will be? Parallel. If this is our first capacitor, its capacitance is C1. This is our first plate and this is second plate. So next is this second capacitor, C2. This is our first and this is our second. Then third, its capacitance is C3. This is first, this is second. How these are? In parallel, all the first plates are connected. All the first plates are connected like this. And all the second plates are connected. So then these are connected to a cell whose EMF is this is our positive terminal, this is our negative terminal. So all the first plates are connected to the positive terminal and all the second plates of C1, C2, C3, they are connected to the negative plate. If it is so, such a combination, we say it as parallel combination of capacitors. All the first plates are connected to the positive terminals, all the second plates are connected to the okay. See what happens here? It is as if this cell is directly connected to the capacitor. It is directly connected to these capacitors. C1 is directly connected to V. C2 is directly connected to V. C3 is directly connected to V. Okay. But that was, we were not seeing in the series combination. Only the extreme left and right plates are connected to the battery, to the cell. But here, each and every capacitor is connected to the cell. So that the potential drop across each is same. Potential difference between the capacitor C1 is same as C2 is same as C3 because it is directly connected to the capacitor. So what potential difference we have, same potential difference will be there here. So what potential difference is there? Same potential difference. So exactly same potential difference will be there. So in parallel combination, potential drop across the capacitor or potential difference across each of the capacitor is same. So then what will be different here? The capacitance of capacitor is different. It is C1 here, C2 here, C3 here. So therefore, definitely, so we have C is equal to Q by V. Definitely what it is? V is the same. Then definitely as capacitance changes, the charge on each of the capacitor also should be different. In the sense, if the charge on this is Q1, charge on this will be Q2, charge on this will be Q3. In a series combination, we have seen the charge on each of the capacitor is same. But here on capacitor C1, charge is Q1. On capacitor C2, charge is Q2. On capacitor C3, charge is Q3. Whereas potential difference across each of the capacitor is same, and it is same as what EMF of the cell. What is the EMF of the cell? It is equal to, this potential difference is equal to the EMF of the cell. Okay, followed. So it is 3 capacitors. How we write it? 3 capacitors C1, C2 and C3 are connected in parallel. How it is? The first plate of each capacitor is connected to positive terminal. Second plate of each capacitor is connected to negative terminal. It is in such a way that the each capacitor are directly in contact with the cell. Therefore, potential difference between these capacitors, between each of the capacitor is same. So that the charges on each of the capacitor is different. How it is? They are directly proportional. More the capacitance, more will be the charge. More the capacitance, more will be the charge. They are directly proportional. If C1 is more, Q1 will be more. So like this, more the capacitance, more will be the charge on. So that, how I write the expression for, so this is charge. It will be Q1 is equal to, what it is? It is a C1 into V. Q1 is equal to C1 into V. Q2 is equal to C2 into V, and charge on third capacitor is equal to C3 into V. Okay, so that the sum of the charges Q is equal to Q1 plus Q2 plus Q3. It is equal to, it is C1V plus C2V plus C3. So this will be V into C1 plus C2 plus C3. So this Q, so this Q by V is equal to, it is C1 plus C2 plus C3. Call this as equation, this as equation 1, this as equation 2, and this as equation 3. So these are the, by using the formula of capacitance, I have found what is the charge on each of the capacitor. Charge on first is C1 into V, charge on second is C2 into V, charge on third is C3 into V. Then what is the net charge? Sum of the charges in each of the capacitor. What is the net charge? It is Q1 plus Q2 plus Q3, which is like this. So Q is equal to V into C1 plus C2 plus Q by V is equal to C1 plus C2 plus C3. So now we have a capacitor. We have a capacitor. We have a capacitor whose capacitance is Cp. Whose capacitance is Cp. So it is an equivalent capacitance. Its capacitance is Cp. When you apply a potential difference of V, so it will store the charge Q. What? The sum of all the charges can store. What sum of all the charges, all the capacitance can store? It is storing in one capacitance only when same potential is applied. When same potential is applied. What capacitance, what charges on each of the capacitor can store? Sum of the charges stored on each of the capacitor. So this one capacitor will store when you apply a potential of V. Then what I say, this Cp is, it is equivalent to these three capacitors when they are connected in parallel. So if I write for this, how it will be? So I am writing that Cp is equal to what it is? It is Q by V. The net charge The sum of all the capacitors, what charge they can store? Net charge by V. Cp is equal to Q by V. Say this as equation 4. So if I substitute 4 in 3, if I substitute 4 in 3, 4 equation 4 in 3, if I substitute, what I am getting? In place of Q by V, I will substitute it as Cp. P refers for parallel. Cp is equal to, it is C1 plus C2 plus C3. So this is our expression for the equivalent capacitance when they are connected in parallel. Cp is equal to C1 plus C2 plus C3. So what are the things we have observed in the parallel combination? The potential difference across each capacitor is the same, that is 1. Okay, and because of that, the charges, different charges will store on the capacitor. That depends on the capacitance. More the capacitance of the capacitor, more will be the charge. So what are the things we have observed in the parallel combination? First thing is Cp is equal to C1 plus C2 plus C3. The equivalent capacitance when they are connected in parallel, it is sum of the capacitance of all the capacitors. Sum of the capacitance of all the capacitors. What we have seen is in a series, it is the reciprocal of the series capacitance is equal to sum of the reciprocal of all the capacitance. Whereas here, the parallel Cp, so equivalent capacitance is equal to sum of the capacitance of these capacitors. This is first thing. What is the next thing? Second thing, potential difference across each capacitor is the same. Potential difference. across each capacitor is same, and what it is, and is equal to EMF of the cell. So then third thing, the net charge on the combination is equal to Q is equal to Q1 plus Q2 plus Q3. And next thing, so this charge stored on the capacitor is directly proportional to the capacitance of the capacitor. So charge stored on capacitor, stored on a capacitor is directly proportional to capacitance. More the capacitance, more will be the charge. And one more thing, what we can observe, if its capacitance is, first capacitance is 1, second capacitance is 2, so what it will be, third capacitance is 3. What is equivalent capacitance? 1 plus 2 plus 3. As I take an example, in the series combination, in the same way I am taking here also. If this is of a capacitance 1, for example, we take 1, 2 and 3. The equivalent capacitance, when we see Cp is equal to, it is 6. What you are seeing here, the equivalent capacitance is greater than the greatest among them. So among them 3 is larger capacitance. It has got larger capacitance. What equivalent capacitance we get? So that equivalent capacitance is larger than the large among them, greater than the great among the capacitors. It is greater than the larger among them. Isn't it? So that's what we are saying there. In series combination, it is smaller than the smallest among them. It is here greater than the greatest among them. Among 1, 2, 3. You can see any example you can take and you can see. It is greater than the greatest among them. So this is equivalent capacitance. Is greater than greatest among them. It is greater than the greatest among them. So these are the things what we are seeing in a parallel combination. So same thing if you compare. So what 5 points we have given in the series combination and what 5 points it is there in the parallel combination. If we compare, so that itself becomes the comparison between the series combination and parallel combination. So what we are observing is Cp is equal to C1 plus C2 plus C3. If these are equal, if C1 is equal to C2 is equal to C3 is equal to some C. So what it is? Cp is equal to C plus C plus C. In the sense it is 3C. If there are just two capacitors in the parallel combination, C plus C is 2C. So in this way, if n capacitors are there, if n capacitors connected in parallel, if n capacitors are there, n equal capacitors, in fact, n equal capacitors, n equal capacitors are there, then what we are seeing, Cp is equal to, it is n times of C. Cp is equal to n times of C. There in the series it is C by n, equivalent capacitance. If n equal capacitors are there, there it is C by n. Whereas here, if n equal capacitors are connected in parallel, it will be n into n times of C. N into C. Okay. So what usually they ask in the problems, as the potential among each of them is same, they ask you to find out the charge stored on each capacitor. The charge stored on each capacitor, they ask. So for that, we have C is equal to Q by V. Q is equal to C into V. So for first capacitance, Q1 is equal to, it is C1 into V. Since the potential difference is the same, just I write it as V. So what is the expression for equivalent capacitance? So charge stored on it is Q. Charge stored on it is Q. It is Cp into Cp into V. Q is equal to Cp into V. So what we have? V is equal to, it is Q by Cp. So if this value of V, if I use here, Q1 is equal to, it is C1. In place of V, I will substitute Q. Q by C. If three such capacitors are there, then Q1 is equal to Cp value, it is C1Q whole divided by C1 plus C2 plus C3. So Q2 is equal to, similarly, we can write Q2. What is here? If Q1, then there is a C1, the net charge. So it is C2 into Q divided by C1 plus C2 plus C3. Q3 is equal to, it is C3 into Q divided by C1 plus C2 plus C3. So using these things, you can find out the charge stored on, if capacitance is given, so you can easily find out the net charge. If net charge, you know, capacitance is given, so how the charges will distribute, among different capacitance, you can find out in this way. You can find out in this, what is the charge on Q1 and charge Q2. So using this shortcut, you can find out. One
hour. 1 hour.
So by this, we'll stop here, and tomorrow, in fact, on Monday, we will start some numericals based on this. Okay, thank you.